Hello embedded geeks. Welcome to the second part of this tutorial video on AURIX GTM. In the last video, we saw the internal architecture of AURIX GTM in detail. Today, we will do a practical demo using a few subunits of GTM. This will give a feel for you how to configure subunits and use this module for your applications. With this knowledge, you can configure any subunits of GTM for your own application. Today's our agenda. We will quickly recap some important points. Then let's do a demo on generating PWM using TOM module and capture the same using TIM module. Let's see how accurately TIM captures the duty cycle and period. Second, we will generate a PWM using ARU-connected TOM, Atom, using interrupts. We are using Infineon sample codes for this demo here, thanks to Infineon library. Welcome once again to COCOWATT. What did we learn in the last video? We saw this architecture in detail. We saw each subunits, its functionality, very detailed. If you haven't seen that video, please see that first. Here, GTM is a modular timer unit designed to accommodate many time applications. TIM is responsible for filtering and capturing input signals of the GTM. Clock management unit is responsible for clock generation. The configurable clock generation unit CFGU provides 8 clock sources to the GTM submodules like TIM, TBU, monitor, and Atom. Fixed clock generation is another subunit of CMU, clock management unit, and it provides 5 predefined non-configurable clocks for GTM modules, including TOM. TOM, timer output module, it can offer 16 independent channels to generate output signals. Let's see a demo with these subunits. Demo 1. As we mentioned, timer input module TIM of the GTM is used to capture an external PWM signal and calculate the PWM signal frequency and duty cycle. Here, for demo purpose, we will generate the PWM using TOM submodule of the same AURIX microcontroller and will externally connect to TIM module. Here the setup is like this. For generating PWM signals, we will use P0 to 03, port 02 we will use, and the third pin in the port 2. We will configure it as a TOM output port pin. We configure 0th pin of port 2 as the input pin of TIM module. Now let's go to the coding and we will see how this is achieved. So in this project, we use TC275 board. It has 3 cores. Corresponding to 3 cores, there are 3 main functions also. So we implement our logic in CPU 0, core 0. So this is the main function, core 0 main function. Here, the first part, this is some generic functionality. We are disabling the watchdog because we are not servicing the watchdog in our example code. And we are enabling the tick timer. These parts in detail we will see in another video. These are some something specific to the controller. So we will come to our implementation. So first we have to initialize the TM. Init TM is done within this function. We can see what is done within this function. Here first enabling the GTM. We call the function if GTM enable to enable the function, then we'll enable the clock by calling this function if GTM CMU enable clock. Then we initialize an instance of ifgtm config structure. So this structure has so many default parameters. All these parameters we will able to configure it. Finally, we will initialize it. We can configure the input pin type, it's PWM in, and input pin port we are able to select, and if we go with inside the structure we can do. What is done within these functions? For example, if you take the IFS GTM enable function, see, in a register, something is written. So how we know what need to be updated in these registers? This we have to know from its data sheet. We have to read the data sheet properly. So this particular one we'll check. So in generic timer, we will see the its generic register implementations. So here clock control register. Within clock control register, to enable this, we see we have to write 0. So to disable 1. So this is what we write in our driver program. So we don't write this driver program. We use the Infineon low driver ILDD Infineon low level driver codes. So here we can see in our enabling function within this register we write 0. So this is how we implement these functions. If you see one more example, CMU enabled clocks. So if we come to this function, we can see under GTM there is CMU module. CMU module there is a clock enabled register. Clock enabled register we write a value clock mask. So what is the meaning of this? We can see in the data sheet. We will go to the CMU module. Where is the CMU module? Yeah, clock management unit. So in this clock management unit, we'll come to the register implementation. There is clock enabled register. We will go to clock enabled register. If you see to enable the clock, we have to write 1 0, that is 2. Remain to provide reset the register enable, but we have to enable the clock, so we have to write 2. So we will see what is the value of clock mask here. So clock mask, this is the parameter as a clock mask. So if we go to its definition, why it's not going to definition? Let's see. Yeah, okay. So here is the value 2. 2 is equivalent to 1 0. So this is how we are doing this implementations of each register. So initting, this is how each functionality is implemented. Now, next one, we have to configure the TOM. Configuration of the TOM is done generate PWM function. So in generate PWM function, we can see first we enable the FXU clocks by calling the function ifgtm cmu enable clocks. Then initialize the instance of the structure ifgtm tom PWM config. Here we have the possibility to here also we can see there is a register. The register, the intended value will be written to enable this clock. So if you come back to the generate PWM function, a moment. Yeah. So in tom config, see there are many parameters we will be able to configure it. Tom, tom channel, period, duty cycle, pin out, pin, system peripherals, clock. All these features we will be able to configure, and finally we have to initialize it. Now what we are going to do in this SPM, we are going to generate a PWM waveform. So what will be the period of this waveform and what will be the duty cycle of this waveform? That is defined here. Let's see what is PWM period. A value is written as 50,000. What does it mean? How will we calculate the frequency of this waveform from this value? Let's see that. The FXC clock frequency, that is the frequency for this TOM module, is 6.25 megahertz. So time period is 60 nanosecond. So if this 50,000, if we divide, we will get 8 millisecond. That is in every 160 nanosecond timer will be updated. So yeah, so 8 millisecond will be the period of the waveform what we are going to generate. So code is ready. Just let us just build and flash the project. we have to wait. Yeah, now we will go to our debug window. We have to change the perspective to debug perspective. Here, these are the two variables which we are going to monitor. We'll just, flashing is over, we'll just refresh. Yeah, see. So what is the time period we configured? 8 milliseconds. So corresponding frequency is 125 hertz, and duty cycle is 1 by 2, that is 50%. So this is captured accurately here. Now let us try changing this period a little and try whether that is capturing properly here. Let's go back to our normal perspective. Yeah, here C bar C++ perspective. Here let us just change this PWM period value, tick value. Let us change to 10,000. That is period we are reducing to 1 by 5. So frequency we expected to be increased by 5 times. So 125 into 5, we expect a PWM period of 625 and duty cycle 25. Let us see this. Yeah, we'll go to debug perspective. Yeah, we will reset. Yeah, see, 625 and duty cycle is detected correctly as 25%. Now let us move on to our second demo. In second demo, GTM atom is configured to trigger an interrupt every 500 millisecond. The interrupt toggles an LED. Means the generator timer module triggers an interrupt every 500 millisecond. We have a LED 1 connected in our board. This will be toggled inside an interrupt service routine. Let us go to the coding. So in this example also, we implement the functionality in core 0. So here there is a init function, init GTM atom. Within this, we will configure the atom module. First, what do? We set this enabling the GTM as like in the previous example. We call the function ifgtm enable. Yes, the function ifgtm atom timer init config. This initialize an instance of the structure atom timer config. This particular structure contains different parameters to configure the atom. We select atom 0 and timer channel, we select channel 0 and clock CMU clock 0. Base frequency has 2 hertz because we need an interrupt in every 500 millisecond, right? And ISR priority and ISR provider we will be able to configure here. Now we have to configure the input pin, that is also done here with this function ifs port set pin port output. So here we configure the output mode as push pull and the LED 1 of the board. We use it for this particular demo purpose. Here we start the atom timer. Just by enabling, we will start generating the PWM waveform. So here we defined the pin LED pin. Now we have to define the interrupt service routine. Using this function, we define this ISR, its vector number and its priority. Now within the ISR, we have toggling our LED pin and timer acknowledged timer IRQ. This normally clear the IRQ flags, interrupt flags. So now let us go to the demo. So this project, yeah, we will build this and flash to our board. Building it, flashing started. Okay, now let's see the board. So here we can see the LED 1 pin is toggling. So our program was to toggle this LED 1 in every 500 milliseconds. So this we achieved. Thanks for watching this. Let's meet again with another video.